Good evening, everyone. So in the last lecture, we discussed about the magnetic dipole moment, right? And where we discussed how we calculate the magnetic dipole moment for different shapes of conductors, right? And we also found that magnetic dipole moment, how it actually depends upon the effective length between the two poles of what we call as two poles of the conductor, right? Now, today in this lecture, we'll be discussing more about the magnetic moment of current carrying coil, right? Or current carrying loop. So current carrying loop always acts or behaves like a dipole also, right? The current through the loop is flowing in the anti-clockwise direction. Then the front face of this coil will behave as the north pole and the back side of this coil will behave as the south pole of the dipole, right? And similarly, if the current is flowing in the clockwise direction, then the clockwise direction will represent actually a south pole of a coil, right? And the back side of this coil will represent the north pole of a coil, right? So this behaves as a magnetic dipole, right? So the current carrying coil actually behaves like a magnetic dipole, right? The face of coil in which current appears to flow anti-clockwise acts as north pole, and while the face of coil in which current appears to flow clockwise acts as south pole, right? You can see here in this diagram also. Here in this diagram also, you can see this is an anti-clockwise current, right? This is the anti-clockwise current. And this face will behave as the north pole of this dipole, right? And similarly, this is a clockwise current here. It means this face is going to behave like a south pole of a magnetic dipole, right? So magnetic moment is actually an axial vector, right? The direction of the magnetic moment is given by the direction of the axial vector, or we can say it's given by the direction of the area vector, right? And we know that area vector is a vector associated with some surface area, right? And the direction of magnetic movement is always along the direction of this area vector, right? So we define magnetic movement as it's the product of this current I flowing through this area, right? And the area vector A, right? So the direction of this magnetic movement vector will be given by the direction of this area vector, right? You can see here that the current is flowing in the anti-clockwise direction, right? The current is flowing in the anti-clockwise direction. Then it means that the direction of this magnetic movement will be out of the plane and perpendicular to this plane, because axial vector or the area vector is perpendicular and out of this plane, right? Similarly, for this case here, the direction of the magnetic movement vector, right, is into the plane, right? It's into the plane and perpendicular to this plane if the current flowing through this loop is a clockwise current, right? So magnetic movement vector is always perpendicular to the loop, right? It is always perpendicular to the loop. We can also find the direction of the magnetic movement vector if we curl our fingers, right, using the right hand thumb rule. If we curl the fingers along the direction of the current, then the thumb points in the direction of the magnetic movement, right? The thumb points in the direction of a magnetic moment. So this is how we can actually find the direction of the magnetic movement vector using the right hand thumb rule also, right? If we know the direction of the current, we can find the direction of the magnetic moment, right? Or we can also find the direction of magnetic movement using the direction of the area vector, right? It's a vector quantity, right? It's an axial vector, right? It's an axial vector. And the units of this will be ampere meter square, right? Ampere meter square will be the units of this magnetic moment, right? Now let's try to calculate this magnetic moment vector for different cases here, right? You can see here a wire of length. Actually, the wire of length is L here, right? It's L. carries a current bent into various regular polygons shown below, right? You can see here we have a wire of length L. We have bent it into different shapes, right? Or different shapes of regular polygons, right? We have a square, regular, hexagon, we have square, circular loop, and we have also an equilateral triangle, right? And we have to find the magnetic moment, right? So you can see here, the first diagram we have is the equilateral triangle. So if we want to find the direction of this magnetic moment vector, right? If we curl our fingers of our right hand along the direction of this current, right? Then the thumb perpendicular to this plane will actually give us the direction of this magnetic moment vector, or we can say it's out of the plane of this triangular area and perpendicular to it, right? And the magnitude of this magnetic moment vector will be given by the current is flowing through this loop, that's I, and the area of this triangular area, right? Triangular portion. And the area of this triangular portion is, let's suppose this is A, this also has to be A because it's an equilateral triangle, right? If this is A, right? Then if we draw this perpendicular to this face, right? So this part will be A by 2, right? If this is A by 2, then this altitude or this perpendicular of this triangle has to be equal to, it will be under root of A square minus A square upon 4, or we can say it will be root 3A upon 2, right? Root 3A upon 2. So this will be the length of this altitude here, right? So the area of this triangle will be half base into altitude. The base is A upon, the base is A and the altitude is root 3A upon 2, right? Root 3A upon 2. So the magnetic moment has the magnitude equal to M A square multiplied by this vector root 3 over 4. So this is the magnetic moment for this triangular loop, right? For this triangular loop. And similarly for this rectangular loop, you can find the magnetic moment vector will be equal to, the current is I, right? And once again, the direction of this magnetic moment vector will be perpendicular to this rectangular plane and out of this plane, right? So this will be the direction of this magnetic moment vector actually, right? This is the direction of this magnetic moment vector, and similarly, this is the direction of this magnetic moment vector, right? Right? So the area of this what we call as area of this triangular rectangular loop here will be, we know that total length of this rectangular loop is actually, total length of this rectangular loop has to be equal to L, right? Has to be equal to L. So this is L, this is the total length of this rectangular loop, right? And we know that the perimeter of this rectangular loop is, let's suppose B is the height of this loop, right? So it has to be equal to twice A plus B, right? Twice A plus B, or we can say that the value of B will be L upon 2 minus A. So this will be the value of B, right? This will be the value of P. So the magnetic moment has the magnitude for this case equal to current I, right? This is current I multiplied by area. So area will be actually length A multiplied by the breadth B, that's L upon 2 minus A, right? So this is how we can calculate the magnitude of this magnetic moment vector for this case, right? And similarly for this case also, this is a hexagon here, right? This is a hexagon here, right? This is a hexagon here, right? And we know that the length, the side of this regular hexagon here is equal to A, right? And we also can find the magnitude of this magnetic moment of this hexagon, that's current multiplied by the area of this hexagon, right? And the area of this hexagon can be found. You can see that this is one triangle, right? This is another triangle, right? This is the third triangle, and this is the fourth triangle, and this is fifth triangle, right? So the six triangles will be created, right? Six triangles will be created here. So we can easily find the area of this single triangle multiplied by this 6 by a factor of 6. We'll get the area of this total regular hexagon. And then we'll get the magnitude of this magnetic moment for this regular hexagon as well, right? But for this circular loop, the magnitude of this magnetic moment vector will be actually I multiplied by this A, that's pi into R square, right? So this will be the value of this magnetic moment vector, right? Now let's try to find torque to the bar magnet when we place a bar magnet in presence of some external magnetic field, right? If you place a bar magnet in the external magnetic field, then because of the external magnetic field, this bar magnet is actually going to experience some magnetic force. And because of that magnetic force, there can be a translation of this magnet and there can be a rotation of this magnet as well, right? So rotation of this magnet about its axis will be because of the torque due to the external force or due to the external magnetic field present in the region, right? So let's try to find out the torque acting on this bar magnet, right? And we know that if the pole strength for this bar magnet is M, right? Let's suppose the pole strength for this bar magnet is M, right? Pole strength for this bar magnet is M, right? And there is external magnetic field, uniform magnetic field. Let's suppose the magnetic field is uniform. Let's suppose that's P naught, right? Then the force on this magnetic dipole or magnetic bar magnet, right? It will be equal to the strength of this pole strength of this magnet, right, multiplied by the external magnetic field, right? We can write it as pole strength by small m and the external magnetic field B naught, right? So this will be the force acting on this bar magnet because of the presence of external magnetic field, right? Now, because of this force, the bar magnet can translate, it can rotate as well, right? So it can have a translation as well. It can have a rotation as well, right? So if we have to find the rotation because of this external force, right? We have to calculate the torque due to the external force, right? So torque due to the external force, we know it's equal to L cross F, right? L cross F, where F is the external force, L is the perpendicular distance, right? L is the, uh, or we can say L is the perpendicular, we can write it also as L perpendicular into F, will L perpendicular is the distance between the axis of rotation of this object and the line of action. Line of action is the line along which the force acts, right? Line of action is the line along which the force acts on this bar magnet. You can see here there are two force. There is force along this direction. There is a force along this direction. Or we can say that the same amount of force will act on this bar magnet, right? On the north pole, and the same force will act on this south pole as well. Or we can say that the net force on this bar magnet will be zero, right? Because the magnetic field is uniform, right? So we can say that net force on this bar magnet will be equal to zero, right? Because of the presence of uniform magnetic field, right? If the magnetic field is not uniform, if the magnetic field is non-uniform, then the magnetic field at two different points, or we can say at two different poles of this bar magnet will be different. If the magnetic field is different, then the force at two different poles of this bar magnet will be different, and there will be some net force acting on this bar magnet as well. Or we can say that this bar magnet will also translate apart from rotating because of this external force, right? So if the force is uniform, then there will be only external torque on this bar magnet. There will be no net force, or we can say this bar magnet will not actually translate. It will only rotate, right, about its axis, right? Because the net force on this bar magnet is zero because of the uniform external magnetic field, right? So this torque will be L cross F, or we can write it as L times F sine of theta, right? And this theta is the angle between this L vector and F vector, right? L vector and F vector. Or we can also write it as torque is equal to, we can replace this force F by M into B, right? We can write it as L into M into B is the magnetic field multiplied by the sine of theta, right? Sine of theta. This is the magnitude of this, what we call as torque, right? External torque on this bar magnet, right? You can see that we can just write this M into L as well, right? That's B into sine of theta, right? We know that this M is the pole strength here, right? This is the pole strength for this bar magnet. This is the pole strength for this bar magnet, right? And L is the length between the, or we can say it's the distance between the two poles, right? That's the south pole and the north pole. So this L is the length or the distance between, or the separation between the two poles of this bar magnet. That's the L, right? And we know that pole strength multiplied by the distance between two poles of this bar magnet is nothing. It's the magnetic dipole moment for this bar magnet, right? So we can replace this M by capital M, right? Which is the magnetic dipole moment, which is equal to the pole strength multiplied with the distance between the two ends of this uh, bar magnet, right? So we can replace it with M, right? Or we can say that this torque will be nothing. It will be given by M cross B, right? M cross B. So you can rewrite it as also M cross B, right? So the net torque on this bar magnet will be given by M cross B, right? Where M is the dipole moment, right? Magnetic dipole moment, and P is the external magnetic field of this what we call as bar magnet, right? So this is how we can calculate the torque on the bar magnet due to external magnetic field, right? It will only rotate, it will not translate, because there is net force on this bar magnet will be zero, because the force on this bar magnet is given by the external magnetic field multiplied by the pole strength, right? In the same way, when we try to calculate the force on a charge due to external electric field, the force on that charge, static charges, the amount of charge present there in the region multiplied by the electric field, right? In the same way, we have the magnetic magnetic strength here, pole strength, magnetic pole strength multiplied with the external magnetic field, that will give us the force acting on this end of this magnetic bar magnet, right? So net force here is zero, so there will be only non-zero torque, right? Similarly, we want to calculate the torque on this coil or loop, right? On this coil or loop. So you can say that in a uniform magnetic field, we know that the force acting on a current carrying loop, that's TF, or F is equal to, that's given as, in a uniform magnetic field, that's I times integral of dl cross cross B vector, right? That's the force acting on a current carrying conductor in presence of external magnetic field, right? So this is the force on this coil loop, right? But this coil loop has been placed in a uniform external magnetic field. So this B is actually a uniform field, right? This B is actually a uniform field. Uniform field. So it means that we can just take this B outside this integral, right? We do not have to integrate this B because it's a uniform, or we can say it's a constant in magnitude as well as direction, right? And we have to integrate this dl vector, right? Since this is a closed loop, or this is a coil, right? It doesn't matter whether it should be a circular loop or irregular loop, right? Even if it's a irregular loop, then the closed integral of this dl vector will be equal to zero, right? That's what the polygon law of vector says, that if we have a closed line, closed loop, right, and we have to do the vector integration of that loop, then the vector integration of that closed loop will always be equal to zero, because each and every uh, vector element will be cancelled out by the other vector element within the loop, right? So B is uniform here, or constant magnetic field, right? Constant field. So we'll take this outside, or we can say that F will be equal to I integral of dl, and this is a closed loop. We'll just write it as a closed integral, right? Cross B vector, right? Cross B vector. Now this closed integral of this dl vector is nothing. It's equal to zero, right? It's equal to zero, right? Because of the polygon law of vectors, right? Okay, right here it's the polygon law of vectors. Polygon law of vectors. So closed integral of this dl vector will be equal to zero, or we can say that the net force on a closed loop in presence of external uniform field is always equal to zero, right? If the loop is closed, the net force on this will be equal to zero, right? If the net force is zero, right? Net force is zero, but the torque on this loop will not be equal to zero, right? Torque on this loop will not be equal to zero. Then the torque on this loop will be equal to, torque on this loop will be given as, it will be equal to magnetic moment cross produced with the external magnetic field. So the torque on this current carrying loop will be magnetic moment multiplied cross produced with the magnetic field vector, external magnetic field vector, right? So for this current carrying loop, if this is the direction of this magnetic moment, right? This is the direction of this magnetic moment vector, right? M vector, and this is the direction of the magnetic field vector, right? And let's suppose this is the theta is the angle between the P vector and M vector, then magnitude of this torque on this loop will be written as m b sine of theta, right? M b sine of theta, right? And the value of this m is nothing. It's given by the current I multiplied by the area of this current carrying loop, right? So this is the torque, net torque acting on this coil or loop, right? Let's try to solve this question here. A magnet of magnetic moment 50 I cap, right? Placed along x-axis, right? So a magnet of magnetic moment of 50 I cap. So we can write m vector as 50 I cap, right? 50 I cap. And it is placed along x-axis, right? Here magnetic field vector is given as 0.5 I cap plus 3 j cap, right? Now we have to find the net torque on the magnet, right? The net torque on this magnet will be given by it will be given by m cross b, right? M cross b. That will be 50 I cap cross producted with this vector, that's 0.5 I cap plus 3 j cap. And we know that we can use this cyclic rule for the cross product of the unit vectors, right? So I cap cross I cap will be a 0, right? Because the two unit vectors are along the same direction, so I cap cross I cap will be 0, right? And similarly, we have I cap cross j cap, and I cap cross j cap will give us k cap, right? So it will be 50 into 3, that will be 150 k cap, right? So this is the net torque on this current carrying loop, right? On this magnet, right? That's of magnitude 150, and the direction is given by this k cap unit vector, right? Now have a discussion about, or let's try to learn about the galvanometer, right? Moving coil galvanometer. So it's a very important topic, right, with respect to exams, right? So we'll be discussing this, how actually galvanometer works and what is the principle, right? Working principle and different advantages of this moving coil galvanometer, right? And how it actually works, right? So in the construction part, you can see that we have this coil, right? It consists of a coil, right? And this coil can have n turns, right? And this coil is free to rotate about a fixed axis in a uniform magnetic field, which is radially directed, right? So what we do is that you can see that we have a cylindrical soft iron core. This is a cylindrical soft iron core, right? Soft iron core. It's a magnet, right? And the curvature of this external magnet is in such a way so that the magnetic field over this coil is always in a radial direction, right? It's in a radial direction, so that the angle between the magnetic field vector and the magnetic moment vector is always equal to 90-degree, right? So as to get the maximum torque on the current carrying loop, right? So as that maximum torque acts on the current carrying loop. So this is the reason to have a radial magnetic field here, right? So the only reason to have a radial magnetic field here is to maximize the angle between the magnetic moment and the external magnetic field, right? So the external magnetic field, because of this curved shape of this magnet, the external magnetic field is radially directed towards this loop, and the magnetic moment of this loop is perpendicular to this magnetic field, so as to the so that the torque between the two is maximum, right? So there is a maximum torque on the coil, right? And apart from this coil is attached with a spring, right? With some spring constant or stiffness, right? It's attached with a coil, right? Spiral spring, which always tries to resist the rotation of this coil when the torque acts on this coil, right? You can see here the magnetic field vector will be radial in direction, right? It will be radial in direction, right? So it will be radial in direction. The magnetic field vector will be in radial in direction, and this coil, when the torque acts on it, it will try to rotate because of the external magnetic field about its fixed axis, right? And when it rotates, then spring also comes into play, right? Spring also comes into play, and the rotation of coil is resisted by the extension of this spring, right? And we can see how we actually can scale, how we can actually scale the measurement of this current, right? It means that more the current flowing through this coil, the more will be the magnetic movement, right? And greater the magnetic movement and greater will be the torque acting on this. If the torque acting on this current carrying loop is more, it means that the deflection in this needle will be more, or we can say that it can actually linearly measure the amount of current flowing through the circuit, or we can say that we can actually measure the current on a linear scale, right? Because of this deflection, right? So let's see how actually it works. So this is the construction of this moving coil galvanometer. It consists of soft iron core. It also consists of what we call as moving coil, right? Which rotates about a fixed axis, right? And then we have a spring also attached to it, which always resists the rotation of this coil, right? Now let's talk about the working principle of this moving coil galvanometer, right? So we know that the torque acting on this moving coil is actually given by m cross b, right? It's m cross b, m cross b, where m is the magnetic moment, right? Let's suppose there are n turns present in this coil, n turns of coil, right? Then the magnetic moment will have the magnitude that will be equal to n into I into A, right? N into I into A. So this will be the magnitude of this magnetic moment, right? And the magnetic field has the magnitude of P naught, right? Let's call that as P naught. Then m cross B will be equal to mb sine theta, right? We can write it as mb sine of theta, right? Or we can write it as NIAB sine of theta, right? And we know that this magnetic field vector is radially directed, so that the angle between this area vector and this magnetic field vector is 90 degree, or we can say that this sine theta is nothing, it's actually sine of 90 degree, that's equal to 1, right? That's equal to 1. So that the torque on this moving coil is actually maximum, right? So the magnitude of this torque is nothing, that's given by the NIA into B, right? This is the torque on this coil, right? And because of this torque, there will be the external opposite torque because of the spring also, right? Once the needle rotates because of the torque of magnetic field, right? Then the spring will also resist the rotation of this coil, right? So the torque because of the spring will be in the opposite direction, right? And that torque due to spring, let me call that as tau s, that will be actually proportional to the rotation, right? That will be proportional to the rotation. That's theta, right? Or we can say that this tau s is actually equal to c theta, right? So where c is the restoring constant here, right? So theta is the deflection of this needle, right? Now once this torque, once this coil rotates, then after some time this torque because of the external force will be balanced by the torque because of the spring, right? Or we can say that once the needle stops, this torque NIAB will be equal to c theta, right? NIAB will be equal to c theta. It will be equal to c theta, right? It will be equal to c theta. Or we can say that deflection theta is nothing. It's NIAB upon c, right? We can see here clearly that the current I is actually a direct measure of this deflection, right? The current I is actually a direct measure of this deflection theta, or we can say that it linearly varies with this deflection theta. It means that greater the deflection for this coil, greater will be the current. Then we can accordingly calibrate this scale, right, to measure the actual current flowing through this coil, right? So this is how actually the galvanometer works. You can see that the current measurement of the current is proportional to the deflection, right? So if we calibrate this deflection on a linear scale, then we will be easily able to calculate the magnitude of this current flowing through this coil, right? So I is directly proportional to theta. So this is the basic principle of working, right? Working principle for this moving coil galvanometer, right? Now there are specific terms, right? Some definitions with respect to moving coil galvanometer. The first definition is the current sensitivity, right? Current sensitivity. Current sensitivity, we define it as the deflection per unit current. How much deflection is there per unit current? It means that if galvanometer is more sensitive, it means for a very shorter current, it will produce a large deflection, right? It will produce a large deflection. If the galvanometer is a very sensitive device, right? It means that the range of the measurement of the current will be actually very less because of its sensitivity, right? If this device is more sensitive, then it means that we cannot measure large amount of currents through this device because of its sensitivity. And galvanometer is a very sensitive device, right? And similarly, we define voltage sensitivity as the deflection per unit voltage, right? Per unit voltage. So that's the reason we say that galvanometer is used for the detection of current in a circuit. The reason is because of its sensitivity. It's very sensitive to the very small amount of currents, right? The currents of the order of microamperes, the currents of the order of milliamperes can be directly detected using the galvanometer, right? In the previous lectures also we discussed about the how we actually convert a galvanometer into ammeter, right? Where we use a shunt resistance, right? Where we use a shunt resistance parallel to the galvanometer resistance, right? And we convert that galvanometer into ammeter, right? And the ammeter actually measures the large amounts of current. It measures the currents in amperes, 1 ampere, 2 ampere, 3 ampere, right? So if we have a very small amount of current of the order of microamperes, right? Of the order of microamperes. So if we use the ammeter for the measurement or for the detection of that microampere current, then it won't be possible for us to sense that current or to detect that current using the ammeter, right? That's the reason because of the less sensitivity of the ammeter, right? So ammeter actually produces very small deflection for higher amount of current, right? For large amount of current. And in the same way, actually galvanometer actually produces large deflections for a very small amount of current. That's why we use galvanometer for the detection actually, right? And not actually the measurement. If we have to detect the current in some region, we will prefer galvanometer as compared to the ammeter for the detection of a current, right? But the current sensitivity is nothing, it's theta upon I, it's the current, the deflection per unit current, right? And in the same way, we have the voltage sensitivity, there's the deflection per unit voltage, right? Now there are certain advantages for the moving coil galvanometer. The first advantage was that we can actually measure this current amount of current on a linear scale, right? We can use the linear scale to measure the deflection, right? So it becomes easy to detect the current using the galvanometer, right? And one more point is that we can actually alter the sensitivity of this galvanometer, right? We can make it a high sensitivity by increasing the value of number of coils, right? By increasing the external magnetic field strength, by increasing the area of this coil, right? And by decreasing the restoring constant of the spring, right? Because you know that more the number of coils or more the number of turns for this coil, the more will be the magnitude of torque, and larger will be the torque, and larger will be the sensitivity, right? In the same way, we can also increase the current or area of this coil and external magnetic field. But if we have to reduce the sensitivity of this what we call as moving coil galvanometer, then we have to increase the stiffness of the spring attached to it, right? If we increase the stiffness of a spring attached to the needle, right, we can actually decrease the sensitivity of galvanometer, right? So this is the advantage. We can actually directly increase or decrease the sensitivity of galvanometer, right? And one more important point is that since we always use a strong magnetic field uh, for this galvanometer, right? So there is no actually there is a minute or we can say negligible effect on this galvanometer because of the presence of any other external magnetic field, right? Because we usually use a very strong magnetic field, right? Magnets of high fields for this moving coil galvanometer, right? So one important disadvantage for this galvanometer is that sometimes if we use this galvanometer for the currents of the order of amperes, right? So it will very suddenly or very quickly get uh, damaged, right? Because of its high sensitivity. So because of the high sensitivity of this device, we cannot use it for measurement of the large currents because it will be damaged, or it will be all the springs or the coil will get broken, right? Because of its high sensitivity, right? So let's try to calculate how much work done we need to do in order to rotate the coil in the external uniform field from first orientation from some first initial orientation to final orientation. You can see here there are two different orientations here, right? Initially the angle was theta 1 between the magnetic moment in the magnetic field, and the final angle is theta 2. We have to see how much work done we need to do, right, in rotating the coil in presence of uniform magnetic field, right? The work done will be nothing, it will be given by, so the work done will be given by, that will be actually integral of tau d theta. So it will be the integration of this torque, right, with respect to the deflection of the rotation, right? So integrating it from theta 1 to theta 2, so the work done will be equal to, torque is nothing, it's actually equal to mb sine theta, right? Mb sine theta. We can put the value of torque here, mb sine theta. So the work done in rotating this coil from theta 1 to theta 2, or the deflection equal to theta 2 minus theta 1, right? So the torque work done will be actually mb sine of theta, right? D theta with limits theta 1 to theta 2, right? Theta 1 to theta 2, or the work done will be actually equal to mb. Integration of sine theta will be minus cos theta, right? It will be minus cos of theta, right? Minus cos theta with the limits theta 1 to theta 2, right? So work done will be actually mb cos theta 1 minus cos theta 2, right? So this is the work done in rotating this coil from initial angle theta 1 to the final angle theta 2, or we can say that to produce a deflection of theta 2 minus theta 1. The work done is given by nb cos theta 1 minus cos theta 2, right? So what happens to this work done? This work done is actually stored as a potential energy, right? Potential energy of a coil in the external uniform magnetic field, right? So we define the potential energy of this magnetic dipole as work done in rotating the dipole from a direction perpendicular to the given direction, right? So we define it as the work done in rotating the dipole from a given direction, right? From a direction perpendicular to the given direction, right? It means that the work done is given by, we calculate the work done as W, that's equal to MB cos of theta 1 minus cos of theta, right? Let's suppose the deflection, so initial angle theta 1 is actually 90 degree, right? That's equal to 90 degree. And the deflection with respect to this theta 1 equal to 90 degrees theta, right? That's equal to theta. It means cos theta 1 or cos 90 will be equal to 0, right? So W will be equal to MB cos 90, right? Minus cos of theta, right? Cos of theta. And this cos 90 will be equal to 0, right? If cos 90 is equal to 0, we'll be left with work done as minus mb cos of theta, right? Minus mb cos of theta. Or we can also write it as minus times m dot b, right? It's the dot product of magnetic field vector and the magnetic moment, right? So minus times m dot b, right? So this is the work done, and this work done is stored as a potential energy of this magnetic dipole, right? So potential energy in a magnetic dipole is given by minus m dot b. It's a dot product of magnetic moment vector and the magnetic field vector, right? So let's suppose we can see that for theta equal to 0 degree, right? For theta equal to 0 degree, then the work done will be actually minus mb, right? Minus mb. Theta equal to 0 degree. This is the case one for theta equal to 0 degree. For theta equal to 0 degree, potential energy will be cos 0 is 1, that will be minus mb, right? And similarly for theta equal to 90 degree, right? 90-degree rotation. This work done will be equal to 0, right? And for theta equal to 180 degree, cos 180 will be minus 1. The work done will be actually, or the potential energy will be equal to mb, right? Plus m. So here you can see that we know that for a dipole in a uniform external magnetic field, right? The net force on the dipole is actually 0, right? Or we can say the net force on this dipole is 0, right? And the energy for this dipole is actually minimum here, right? You can see the minimum energy for this dipole is at theta equal to 0 degree, right? So the minimum potential energy for this dipole is at theta equal to 0 degree, that's minus mb. So we can say that this is a stable position, right? Stable position, stable equilibrium position, right? Stable equilibrium position, right? Equilibrium position. So, or we can say that the external torque always tries to align the magnetic moment vector along the direction of the magnetic field vector, right? So that's what the external torque does. It always tries to align the magnetic moment vector along the direction of magnetic field vector so as to minimize the potential energy of the system, right? So the minimum potential energy or the stable position for this uh, dipole is actually theta for theta equal to 0 degree, because the potential energy at theta equal to 0 degree is minimum, right? So the system has the minimum potential energy here at this point, right? So we calculate the torque as well, right? We calculate the potential energy of the coil in uniform magnetic field as well, right? So in the next lecture, we'll be studying about different magnetic materials, right? We'll be discussing about the different magnetic materials. We have diamagnetic, paramagnetic, and ferromagnetic materials, right? All those materials will be discussed in the next lecture, and then we'll be starting with the electromagnetic induction, right? We'll be starting the electromagnetic induction. So let's stop here and meet in the next class. Goodbye.